Okay, so it's just time to start. So first of all, can you hear me? And please check these points to fit the presentation. Does your screen fit presentation? And try this sharing menu, upper right corner, view, and outfit. And it's more important. Is your system set up to receive the broadcasted sound? So can you hear me? Please follow these instructions to set up the audio. Okay. So, I'm Motomo Nakashima, presenter today from Tokyo Institute of Technology, Japan. And the host of this webcast is Soren Torholm from AnyBody Technology. And also a panelist is Professor John Rasmussen, also from AnyBody Technology. So first of all, I'd like to thank John and all of AnyBody team to give me such interesting, exciting experience. And they supported me to give this webcast. So thank you, John and AnyBody team. Then you can ask questions using a Q&A panel. So this slide explains how to launch the Q&A panel. You can click this button here and type your questions in the Q&A panel. So you can ask any question by typing. And send a question to host, presenter, and panelists. Okay? And notice the answer displays next to the question in the Q&A box. And you may have to scroll up to see it. Okay. Then, yeah, before my self-introduction, can you hear me? If you have any problem with sound, if you can't anything, please ask Q&A panel. Please ask questions to the host, presenter, and panelist by a Q&A panel. Okay. Maybe I hope everyone can hear me. So, let me introduce myself shortly. I'm Motomo Nakashima, and I got Doctor of Mechanical Engineering 1995, so about 12 years ago. And I'm now an associate professor at Tokyo Institute of Technology. And I'm working at a graduate school of information science and engineering and Department of Mechanical Environmental Informatics. This is a little bit unusual name for mechanical engineering, but at this department, some more simulation-oriented studies, like simulation-oriented study in mechanical engineering is studied, and we are teaching about such kind of mechanical engineering. So basically, I'm a mechanical engineer and teaching mechanical engineering. And this slide shows my present research fields. My main field is biomechanics, so-called biomechanics, and in particular, I'm focusing on some sports such as swimming and skydiving, and I'm also interested in sports injury. And my another research field, actually it overlaps a bit, is the sports engineering. So we are developing some new instruments for sports. Okay. So again, can you hear me? If you can't, please ask by using Q&A panel. And you can ask any question, and you can also ask any question during presentation. I will not see any your question during my presentation. After that, after the presentation, I will check all your questions. So if your question doesn't disturb my presentation, so feel free to ask any question by using this panel. Okay? So, today's topic title is Development of a Musculoskeletal Simulator for Swimming. And so we actually developed a simulator for human swimming. And this work was mainly done by Mr. Yugo Motegi as his master thesis, and he already graduated master course, and he is now working in Nissan motor company, maybe you know. And this work was also presented at the International Symposium on Computer Simulation in Biomechanics, ISCSB 2007 in Taiwan on the last June. So then, in this symposium, John and I talked about this study, and then John kindly invited me to this webcast. And the manuscript of this paper is available at the SWUM's website. I will explain SWUM later, but SWUM's website. So maybe in this presentation, I will use this website several times. So I will introduce all of you this website. Yeah, this site. URL is very simple. www.swum.org. Then you can find some animations and animation of musculoskeletal analysis, and you can also see that some references, and so you can download the manuscript of today's topic from here. Okay. So this is the content of today's topic. Firstly, I'll explain introduction, background, and objectives of this study. Then I will talk about SWUM and SWUM suits. And I will talk about AnyBody modeling system shortly. And then how to integrate SWUM and AnyBody. Then I'll show you some demos and simulation results, and comparison with EMG results, and concluding remarks, and Q&A. Okay. So, again, questions, it is okay to ask anytime. Please launch the Q&A panel here and type your questions in the Q&A panel and send the question to host, presenter, and panelists. Okay. So, introduction. There have been no studies of the musculoskeletal analysis for swimming, although it will provide very useful information for the athletes, the swimmers, the training, and coaching. The reason of this is that the external force, fluid force, acting on the whole body as the input to the musculoskeletal analysis was difficult to obtain so far. But the authors have recently developed a simulation model, SWUM, it stands for Swimming Human Model, which enables to calculate fluid force acting on the whole body. So, the objectives of this study were to develop a full body musculoskeletal simulator by integrating our SWUM and musculoskeletal model, that means AnyBody modeling system, and to conduct a musculoskeletal analysis of swimming and examine the validity of the simulator by comparing the simulation results with EMG results in a previous study. So next, SWUM and SWUM suits. In our model, SWUM, human body is represented as 21 segments as truncated elliptic cones. It's like elliptic cylinders, and like this. And in SWUM, relative body motion, that means joint motion of swimming motion, is given as input, and the fluid force is modeled and computed without solving flow for each part of the body, because it is very difficult to compute the fluid force acting on whole body. Actually, if you use some computational fluid dynamics method, it is so-called CFD method, it will take a huge amount of computing time. So we just using fluid force model. And by time integrating equations of motion for the whole human body, this is we give relative body motion, so this human is can be regarded as one rigid body, changing its form. So we solve the equations of motion for this one rigid body as whole human body. So actually it has 6 degrees of freedom, so it's 6 equations of motion. Then the absolute motion in 6 degrees of freedom, and fluid force acting on each part of the body, and so on, obtained as outputs. So in this simulation example, these red lines from each part of the body represents each fluid force acting on each part of the body. And I will not invoke animation for this simulation result because it is tough to send a movie due to bandwidth problems of this for this webcast. So you can download this animation, these movies. Movies are available at SWUM's website. So you can go to this website using another web browser, and you can see these animations. Actually, it has, let's see, yeah, it has 4 strokes, animations of 4 strokes. So you can download any of this and you can enjoy them. And so you can obtain information about SWUM at its website. And SWUMsuit. Yeah, SWUMsuit is SWUM's implemented software. And SWUMsuit is a free software available on the website of this site. So you can download SWUMsuit for free, and yeah, you can play it soon. Okay. And I will a little bit. I will add some additional explanation for modeling of fluid force in SWUM. It's a kind of it's a topic of fluid dynamics that I'll talk a little bit. In SWUM, elliptic cylinder, this means a body segment. So you can imagine this is a thigh or shank or upper arm or something. And body segment is again divided into thin elliptic plates. So divided along this direction. So there are many tiny these elliptic plates. And fluid force acting on each plate is calculated using its local position, velocity, and acceleration. So it's fluid force modeling. And we consider some inertia force, that means some unsteady effect, and this is quasi-steady force, normal drag force and tangential drag force. So, and these fluid forces act on center of the elliptic plate. So there are many such kind of forces acting on along this axis. And of course, we consider buoyancy, and it acts on a tiny divided quadrangle, or this divided quadrangle. So the surface of the elliptic plate is again divided into these divided quadrangle. And buoyancy acts on a tiny divided quadrangle, or judging whether the quadrangle is below water surface or not. If it is above water surface, of course, buoyancy does not act. And yeah, it's a little bit boring, some fluid dynamics formulations, but you can see that these coefficients, so it has a coefficient. Then we determine these coefficients so that the simulation agrees well with the experiment. And we conducted this experiment. It's just a limb model, and this limb model is moved, it's flapped up and down in water. Then we measure the moment by strain gauges and record it. And then so we can also construct simulation model of this limb model. Then we can we adjusted these fluid force coefficients so that the experimental results agree with the simulation results. Okay. So the details of this part is available on the published paper. Then you can obtain the information of this. This paper. So you can download full paper at the journal's website from here. Okay. So go back to musculoskeletal analysis. So next, AnyBody modeling system. I think many of you here know much about AnyBody modeling system already, but I will explain it shortly. In AnyBody modeling system, input is body motion and external forces, and output is muscle activity. And as you know, all input data are described in any script, so it's actually object-oriented programming language. And we used the full body model with 458 muscles for our simulation. And recently, AnyBody Technology launched a new version of AnyBody modeling system, version 3. But our model is now only for older version, version 2. So next, how to integrate this SWUM and AnyBody. This slide shows the whole data flow, and for SWUM, body geometry and joint motions are inputs like this. And by SWUM, actually it's implemented software SWUM suite, converts body geometry and joint motions for AnyBody modeling system. And the SWUM also outputs body movement, absolute movement of the whole body, and SWUM also outputs fluid force acting on whole body. Then all these data are output in any script format by the SWUM suite directly. So all these data can be directly input directly into AnyBody modeling system. Then you can obtain the muscle activity by using AnyBody modeling system. And this slide shows some additional explanation for fluid force, because fluid force inputting fluid force is a little bit tricky thing. Fluid force, which is calculated at each part of the body in SWUM, is input to AnyBody for 210 points. This figure shows fluid force in SWUM. So you can see that many red lines. These red lines represent each fluid force acting on each part of the body. So these lines, the number of these lines are 210. So we define 210 points for external force in the AnyBody modeling system. So this figure shows the fluid force acting points in AnyBody. So you can see that these red points, on all these points, the force is active. Force is acting. Yeah, it's a little bit different point from other usual calculation. For example, in the simulation of walking or running, fluid force, or external force is acting on only from foot, ground reaction force like this. But for swimming, the external force acts on whole body. So we put these forces, all these forces input to AnyBody. So I'll show you some live demo of the developed simulator. Let's see. You can see that this icon invokes the SWUM suit. So just double clicking, and this is the SWUM suit, our software. And I opened a project folder for SWUM suits like this. Then I am opening the project folder also in Explorer like this. So you can see that three files. These files are input files for SWUM suits. Then by clicking this button, analysis starts like this. Now the analysis engine part of the SWUM suit is running like this. Then you can see that in the project folder there are two folders, and one is just data folder. So the analysis engine is now writing many calculating data for SWUM suit for the simulation. And you can see that another folder in AnyBody folder, and you can see that these files. Yeah, maybe you are familiar with that. Yeah, analysis was completed, and these files are files for AnyBody modeling system. Maybe you already know. And these files are so automatically created by our software, SWUM suit. And you can invoke AnyBody by just clicking this file, main.any, or you can invoke AnyBody just clicking this button from our SWUM suit software, like this. Then, okay, let me change a little bit things. And if you load model, you can start musculoskeletal analysis using AnyBody modeling system. Yeah, it will take some time, I think about 40 seconds. Yeah, it takes some time because it's a little bit large model. It's a full body model. I actually changed the model just into no muscle model. So maybe it takes less than 1 minute. Yeah, this is coming. So, okay. Let's see. Oh, 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 oh. Okay. Yeah, it's a simulation example of closed talk. So you can conduct soon by this AnyBody modeling system like this. Okay. So go back to the presentation. So I'll show you simulation. I'll show you simulation results. This slide shows specifications of simulation results. This is closed talk and swimming motion. And joint motion was created based on a movie on actual swimmer who was an Olympic finalist. So the swimming motion is considered to be very good. And swimming speed is 1.2 meter per second. It is not full strength for this swimmer. And the stroke cycle is about 2 seconds. And we use body geometry of AnyBody's original model in this simulation. And this is a simulation result of closed talk. And in this figure, you can see that T is time non-dimensionalized by stroke cycle. And you can and animations of this movie are available at SWUM's website. Here, so you can download animations for 4 strokes. And this slide shows muscle force around left arm. So this is entry phase for left hand, so hand entry to the water. At that moment, no significant muscle activation can be seen. Then pull phase. This is pulling the water by this hand, so pulling the water in this direction. So pectoralis major at muscles at chest part and lapis dorsi muscle at back is significantly activated. And and at the push phase, this is pushing the water like this by this hand like this. So at this moment, you can see that triceps brachii, which is extensor of knee joint, and so for this, you can see that triceps brachii is activated, significantly activated. And some of you might think this value, 600 Newton is too large for chest gravity. So it will. So maybe it will take further investigation for that. And recovery phase, that means arm outside water. You can see that anterior deltoid, back part of the shoulder, is activated like this. So these activation patterns seems reasonable. It indicates a certain validity of the simulator. So seems reasonable for upper limbs. But however, some of you noticed that tibialis anterior, this muscle is unnaturally activated in simulation. It's actually a problem of muscle model because we use very simple wire muscle model. It doesn't have tendons and ligaments. So in this moment, in actual situation, swimmer doesn't use this muscle, or this muscle seems to be very relaxing, but maybe the movement is supported by a ligament in this moment. But in this simulation, we don't have a ligament, so this muscle is activated. So maybe this also should be fixed in the future study. And we also already conducted simulation for other three strokes, breaststroke, and backstroke, and butterfly stroke. And all animations are available at the SWUM's website, so please check and download these animations from this site. So final topic, comparison with EMG results. And this slide shows a comparison with EMG for muscles around shoulder. Above is simulation and below is EMG measured by Pink et al. 1991. And posterior deltoid and pectoralis major, latissimus dorsi, and trapezius. So you can see that these peaks, the timing of peaks in the simulation and EMG agree well. So it indicates certain qualitative validity of the simulator. Although the swimming motion might be different between the simulation and EMG experiment, because the swimming motion in this EMG experiment was not shown in this paper. So, concluding remarks, a musculoskeletal simulator for swimming was developed. A good agreement between the simulation and EMG indicates the qualitative validity of this simulator. Future study will include a more detailed comparison by measuring the swimming motion and EMG simultaneously for the same swimmer. So actually we are now working on this topic now. Okay, thank you for your kind attention. So, if you have any questions, please ask using this Q&A panel.